or either
Mhm.
of you? How do I actually start this? Let me just share my screen. It's
Yeah.
embarrassing.
No, you're good.
Oh yeah, there it is. View
It says
present.
present.
Weird. Somehow I missed that. Oh, I swear I looked there right just a second
There's
ago. But
also
anyways,
there's also in the upper right-hand corner, there's
mhm.
also a button that says present.
Okay, cool. Gotcha. All right. So I want to talk about neural networks, which is kind of a different approach to machine learning based on uh, artificial neurons, like I believe Jenna talked about in the first one. Um, but this is a little bit of a deeper dive into how they work. So, an artificial neuron is uh, simply a unit that outputs some sort of signal. Um, and it does so by taking in several inputs with a weight attached to each one of them. So I'm going to talk about a specific one, the threshold logic unit, where its output is based on some sort of threshold. Basically, what it does is it adds up all of the weights, or all of the inputs that are weighted. And the inputs could be anything as long as they're numbers in some sort. They could be discrete inputs, they could be not discrete, or and so on and so forth. They could be large, small. It doesn't matter, and there can be any number of them. But it applies some sort of weight to each one. And then it just adds them all together to get some number, and that's the input. The input is just going to be the sum total of all of the input points multiplied by their respective weights. And those weights are what makes the neuron. Finding the right weights to figure out what the output should be is basically what the machine learning part of this is figuring out what inputs are more important, and those so those weights would have a higher magnitude, but then they might be positive or negative based on whether the higher input should create one decision, or lower input should create a different decision. So when learning, it's the specific type of network that I'm going to talk about starts with a bias input, just to give it a starting point for training, so that initially it starts making decisions, and they have to be based on something. So it just always decides that this input is always going to be happening. So it starts making these decisions, and then as it gets smarter, and these vary, it will figure out to ignore the bias that W0 is going to go down, and then the other weights are going to shift to accommodate the input. So the output for the threshold logical unit specifically is going to be based, like I said, on some sort of threshold. So an example here is the very common Heaviside function, where it's just, if the input, the sum total of the inputs is less than 0, it's going to output 0. And if it's greater than 0 or equal to 0, it's going to output 1. So that's pretty much, in my experience, the most common type. And it's also a very simple and easy to understand type. So basically, like, you look at all the inputs, and if they're greater than 1, then, or greater than 0 total, then it's going to output 1. And then if they're less than 0, it's going to output 0. Yeah, so if you put all of these together, if you put many TLUs together, it creates a perceptron. So I probably shouldn't have said many, because you can have a perceptron with just a single TLU, and that still counts. But a single layer perceptron is going to have one TLU for each output, and it's going to be, each one is going to be connected to every input. So it's going to have all the information for each one, but the information may not be relevant for each one. So ideally, as it learns, it'll weight those, the weights of those will approach 0. And then each time it, in order to train it, it's going to keep making predictions. And each time it makes an incorrect prediction, it's going to reinforce the weights that would have contributed to the correct one. So we have this equation here, which is, a lot of math to be thrown at you all at once, or a lot of notation. but it's not super tricky. Basically, it's saying, so this particular weight for the next time step, for the next prediction, is just going to be the current one, offset with a certain amount added or subtracted based on the learning rate and based on the difference between the actual result. Whoops, I skipped ahead. Yeah, based on the difference between the actual result and the predicted result. Yeah, times the learning rate. So a higher learning rate is going to make it obviously learn faster, meaning that older data isn't going to matter as much. So learning faster obviously could be a good thing, but the downside is that if your inputs and the results are really sporadic, then you might not actually learn anything. Your weights are going to change too quickly, and it won't be a good predictive model of anything in particular. So any questions about that, the concept as a whole? Cool. You're not going to have that equation memorized or anything like that. And then, to make a full network, you can just stack layers on top of each other. So a single layer perceptron, obviously, like I said, has a single layer, one for each output. But just the simple inputs weighted don't necessarily produce a viable output for really complicated models. But this can often be solved by putting more layers into it so that these inputs are interpreted into something, these other values that have more meaning, and those outputs ultimately make a more informed output. So if you can have many, many layers, and if it has many hidden layers, that's referred to as a deep neural network. And deep is very poorly defined. It changes from, like year to year as computational power and algorithms, get stronger. So it could mean like hundreds of layers. And since it only refers to the number of layers and not necessarily the width of each layer, that can be a little misleading as well. So to start out, let's actually do some programming. So we have the Iris data set from before. Let me bring up a new window for this to keep things organized. And share this. All right, so I'm going to go ahead and make a new REPL here in Python, and I'm going to create it. I'll just call this like Iris Perceptron. Okay, yep, I already have a Iris Perceptron 0 because I was testing that. All right, cool. So if I want to train a neural network, that's something that, a perceptron, that's something that sklearn already has. So I'm going to go ahead and first I'm going to get the Iris data set. So you could use the CSV that you got in the last one. I know, Jenna, you don't have that. But it's such a common thing to want to do. sklearn actually also includes that, so we don't have to worry about that since we've already learned pandas and don't need to go over it. This will load the Iris data set with already label encoded and all that. So I'm also going to import the linear model perceptron. So this is just a very simple single TLU perceptron. So it's 100% exactly that picture that I showed you, where it has inputs and then one artificial neuron and then an output. So it's got a single brain cell, but we're going to make it pretty smart. So with that, we're going to go ahead and get the data set. So load Iris is a function. So I'm just going to go ahead and say load Iris. Are you guys, by the way, do you guys have the REPLs going and you're able to get all this down? Cool. All right. And then I'm going to go ahead and get the input data. So x equals iris.data. And then I'm only going to get the petal length and the petal width. I should probably have this open. I'm just going to go ahead and, yeah. Or let me upload it just so we can have it as reference. Give me a second. You might want to bring that on your computer as well. We're not, yeah, like I said, we're not actually going to use it in the project because we have it inside the Iris data set here, but might as well bring it up so we can figure this out. Let me add or upload. Oh yeah, upload file. There we go. Upload file. Okay. So yeah, so if you recall, this is the Iris data set. So it's got an ID, sepal length, sepal width, petal length, and petal width, and then it uses that to determine the series. So these are the inputs, and then this is the output. So we're going to keep it simple and only have it determine. It's not going to be able to determine which of the three it is. It's just, we're just going to have it because it can only give a binary output. So we're just going to say, is it Iris 0? So is this true or false is what it's going to determine. This is going to be the output. But because it only works in numbers, we're going to convert that to an integer. So yeah, so we're only getting the petal length and petal width for making our prediction. We could use the other inputs as well, but we don't need to. It's going to work just fine without it. And we're checking, is it Iris setosa, the first one? That's the one that got encoded as 0. Cool. Any questions about this so far? All right, so now I'm going to go ahead and just train it. I'm going to create the perceptron. So perceptron classifier is what that's for. And then I'm going to fit it. What did I do wrong? Oh. Cool. And then I'm going to go ahead and make the prediction. And I can go ahead and, put whatever I want in here. So I'm going to say it's going to have a petal length of 2 and a petal width of 0.5. And I cannot spell right now to save my life, apparently. All right. And then we go ahead and print the prediction. So we run it, and it works just like the other. Oh yeah, we gotta wait for it to install the packages and all that. But it works just like the other linear regression models. It just works differently under the hood than some of the other ones we were using. But it should give us roughly the same sort of predictions that the other models gave us as well. So yeah, so as it goes through the data, it will again be applying those weights. It'll have some sort of assumption off in the beginning, a bias for what it's going to try to do. because it doesn't know anything about the data yet. And then as it makes guesses, whenever those guesses are incorrect, it will change the weights to better fit what should have happened. And it changes it a bit by bit. I'm not sure what the default learning rate and such are, until it eventually is able to figure out, until eventually it trains itself on all the data. And by that point, hopefully, the differences between what it's guessing and what the actual prediction is, or what the actual value is, should be pretty close, and it doesn't have to update the weights as often. So like, for example, so I put the petal length and petal width in here as 2 and 0.5. So I said that was not an Iris setosa, most likely. Actually, is that what we want? I'm going to try something different. It might be reversed, actually. So if I put it as something more like, something smaller, I'll just put something that's actually in there, 1.5 and 0.2. Yeah, so it says, yeah, that is, so it says this is probably an Iris setosa. Any questions? Okay, cool. So that's really no different than anything we've been doing before. So I do want to talk about something new, but I first wanted to show how this does fit in. The perceptrons can be used for the same sort of, and neural networks can be used for the same sort of applications as what we've been doing so far, these predictive models. So there are advantages and disadvantages of each. So I could have, like, one disadvantage here is that, like I said, this one has a binary output. So it isn't as helpful to just say, is it Iris setosa or not? We want to know what type of flower it is. And that could absolutely be fixed by just adding another layer onto it, for example, and having the other, or just having multiple outputs would probably be the better way. Just having it say, like, one for, is it Iris setosa or not? And then another for, is it one of the other two or not? And then based on those inputs, you can make a simple, like, logic function just saying, if they're both false, then it must be the other one, or if one of them is true, then output that one. So all we need to do is just add more perceptrons into it, and it'll work just as well. But it is also harder, I believe, to get a degree of certainty from these. It doesn't really have one, whereas some of the other models do have a more measurable degrees of certainty. Any questions? All right, but one of the big advantages of neural networks is their applications in reinforcement learning. So let me go ahead and present this again. So in reinforcement learning, you create an agent, and the agent has to make decisions. So every time it makes a decision, it gets a reward, and that is the term for it, although a reward can be positive or negative. So you can think of it as reinforcement as well. That's, part of what it's called, but the term they use is reward, regardless of whether it's positive or negative. So, you can think of it as it, when it does something, it either gets, rewarded for it, gets happy about it, gets pleasure, or it gets punished for it, receives pain if it does something bad. So it may receive a positive reward for completing a task, and, based on how well it completes a task, but then receive a negative reward for the amount of time it took to do so. And it might continually receive negative rewards as it's approaching and only get its positive reward at the end, or possibly not at all. It doesn't have to necessarily get a positive outcome. All that matters is that it tries to make the best thing possible. So it may only receive negative rewards and just tries to minimize that. So some examples of reinforcement learning are self-driving cars. So what do you guys think would be some rewards it would receive for certain actions for a self-driving car, or for certain results? Any ideas? All right. So it might receive a reward for getting to a positive reward for getting to its destination, right? That's its goal. Or for if each smaller action, it might receive rewards just for how close it gets to the destination. As it approaches its destination, it'll get rewarded, and then it'll get possibly a big reward at the end for getting there. But then it might receives negative rewards for the amount of time it takes, like I said, or for crashing, right? That would probably be a very large negative reward. So it knows to really, really not do that the next time it gets into a situation where it can think, I could attempt to get here faster. I might crash, but should I do it or not? Well, the reward would be scaled to that, so that if it is going to crash or run into a person or something like that, it knows that's really bad and should be avoided at all costs, and won't take actions that might cause that, even if it could receive a larger reward. So a lot of it is about calculating risk as well. So yeah, video game AIs, kind of same sort of thing, right? Gets a reward for winning, might get a reward for how well it wins, and then gets punished for losing, and might get punished for the degree as well, or it might not. There may be some instances, some games where it doesn't matter how much it wins or loses by. It just matters if it wins or loses. And obviously, the amount as it's approaching that point may affect the likelihood of that happening, but it doesn't actually affect the reward itself. So, for example, if it's losing, it may go for riskier plays because it knows that it doesn't matter. It only matters if it wins or loses. It doesn't matter how much it loses by. Yeah, a smart thermostat could get a reward for every moment the temperature is at where it should be, and then gets a large penalty if someone has to actually go and adjust it. And then stock market traders, are another example where the rewards there is a little more concrete. Just how much money does it make, right? Making money is a positive reward. Losing money is a negative reward, exactly associated to the number of dollars. So that's a pretty straightforward reward process. So the question is, how do you actually train it, though? How do you get it to make these decisions? So the agent should be willing to take risks initially. It should try things out to explore what's called the policy space. So the idea is that the decisions that an AI makes, that an agent makes, are called its policy. So based on some amount of inputs, and those inputs could be anything. They could be like physical sensors if it's a physical robot. It could be, just some sort of data. It could be any amount of inputs, and that's how it understands the world space, and that's all it knows about the world space, is whatever its inputs are given to it. It doesn't necessarily have any preconceived notions about what those inputs mean. They're just numbers to it. But as far as what it does, that's its policy, and the policy space is, just all the possible policies it could have. So one option to figure out like what it should do is just to try everything, every possible thing, every possible not only decision, but way of making those decisions it possibly can. But as you can imagine, that is almost always completely impractical. The policy spaces are generally very, very large, even for small problems, because it's every possible way you could possibly consider doing something. And then there are some other examples of more targeted ways to go through these options, and take risks and have some randomness and variation, so different things happen every time, while still ultimately going towards a more optimal policy. So one way is a genetic algorithm, where you start with agents that, again, don't know anything about the world around them, and have some sort of policy that's just randomly generated. You could, if you did have some sort of idea of what the environment it would be working in is like, and something resembling an optimal policy, like hard coded or anything like that, you can try to model the policy after that as a starting point, or they can just be completely randomly generated. But the idea is, you create them and then you test them, you put them in the environment, you let them receive the rewards, and figure out which ones got the most awards. And you take the best ones of those, I think, usually around like 20% of them, and you just kill the rest. The rest are all gone. They didn't make it. So only the best performers survive. And those performers then replace all the ones you just killed by reproducing. So you create some they create new offspring. It can be either asexual or sexual reproduction, but there's some sort of variation and some sort of randomness involved in producing the offspring. And those new agents are going to be obviously based on the best performers with some variation. So just like evolution in the real world, as you make more and more generations, you're going to get closer and closer to an optimal outcome. And then another way to do it is there's something called policy gradients, where you take the parameters, basically your inputs and how you make the decisions on those, and you gradually increase or decrease them to see if the rewards get better when you do so. And yeah, that's a kind of a complicated system in practice, but I think it's pretty easy to understand. You just see if for example, if you're in the self-driving car thing, see if rewards increase when you speed up a little bit in a certain environment, and if it does, you continue to speed up in similar situations, and then until you see penalties for it, and then you stop and see like, okay, this was the good way to go. This was the proper speed. All right, so that's all I have from the presentation. So let's go ahead and apply that. So I'm going to go ahead and go back to REPL. I'm going to make a new REPL. And I'm just going to go ahead and call it, what did I call the original one? Let's call it machine for reinforcement learning. So I was originally going to have us use TensorFlow to train a neural network on this, but turns out REPL doesn't support TensorFlow, and I found that out too late to have you guys like download and install it. So either way, it's going to start out the same. We're gonna be just making our own perceptron and training that through a genetic algorithm rather than using the policy gradient algorithm that we were going to use. But to start out, what I want to use is the GIM library. So you can go ahead and import GIM. You know what, let's just go ahead and import everything we're going to use right now so we can install them, because REPL takes forever to install. So go ahead and just run this with these imports, and we can talk while it's running. But the OpenAI GIM is the longer version of this. It's just called GIM in Python, but this provides a bunch of environments for you to train neural networks on. So there's like a whole ton of them. Like, basically all the Atari games are in there. Pac-Man and the like. And the one that we're going to use is called CartPole, and it's pretty straightforward. You're just trying to balance an upright pole on a cart for as long as you can. You have to make it through 200 time steps, and that's the maximum. If you make it that far, then you are rewarded at the end. So to start out, we're just going to utilize OpenAI GIM. We're not going to make an AI and train on it yet. We're just going to create a basic policy to see how it works. So did you guys get the packages installed? Did REPL get that for you?
It's still going.
Okay. So yeah, we can start typing while it's going
Yeah,
though,
yeah.
and then hopefully it'll be done by the time we actually test it. So the very first thing I'm going to do is make a environment for the AI to run it. So I'm going to go ahead and say gym.make cart pull B1. And so basically every time I, well, I guess first things first, I'm going to have to reset it. So I'm going to say OBS for observation equals env.reset. So it can actually get started, and it'll also tell us what values, it tells us the values that are relevant to the environment. So in this case, the information it receives, I believe, hold on, I don't remember the order, but it's the cart's position. Yeah, I think it's position first, and then the cart's velocity, and then the angle of the pull. And what was the last one? It also had to do with the pull, I think. Let me see if I can find it. Basically, everything I'm getting comes from this book here, which I highly recommend. We're going to have it in the Coder Schools library for coaches to check out as soon as this is done. So if you're interested, then yeah, highly, highly recommend it. I told Ophir she could have first dibs on it though, so once she's done, I guess. Let's see. All right. Oh, yeah. So the first one. All right. Yeah. So it's position first, the car's position, then the velocity, and then the angle of the pull, and then it's angular velocity. So how quickly is the pull moving right this moment? So those are the four pieces of information that we have. But of course, our AI isn't necessarily going to know that directly. We don't have to tell it that. That could make it easier for us, but for the sake of exercise, we're not going to. And then also, if we want to see what it looks like, I can say env.render, and I'm actually going to do that, and I think you guys should do that too, just so you can get the positioning right, because it doesn't like it if you position in the middle. So this just renders one step. You can see it's not moving right now. I'm going to scroll this down. Yeah, that kind of messes it up. But now that the size is adjusted, if I run it again, it should just be fully in there, right there. So it's trying to balance this cart on a pole, and it's just trying to get the maximum reward it can. It gets rewarded by 1 point every frame that it continues. And the simulation can end in one of three ways. Either the pole exceeds a certain angle. It's not a very big angle either. It's like, I don't know the exact angle. It seems like it's only like 30 degrees or so that it can fall before the simulation ends and you lose. You also have the simulation can also end if your cart goes off the screen. But then the other way is just you make it 200 steps. And at that point, you've got the maximum reward. Since you aren't rewarded by how well you do on a specific frame, each frame is exactly one point regardless. And then it's just your total rewards at the end that matters. So how long did you last? To test this out, I'm going to go ahead and make a basic policy. Basically, each frame, in order to go to the next step, we have to tell it what are we getting. So one example of one frame is I'm going to get the observation again. It also gives back the reward. And then it's going to say done, true or false, based on whether we're still going. It's false if we're still continuing. And then obviously true if it's true if it's done and you've lost or won or finished already. And then info, which is not relevant to us at all. But in this particular result, in this particular environment, info is just an empty dictionary. But I believe other environments can have more relevant info, but so we still have to get it since the step returns that. So I'm gonna go ahead and just have it move one once and then render again. And I don't know if we'll even be able to, tell the difference, but just to kind of showcase, this is the idea is by putting in 1, I'm gonna have it move right. And I could put in 0 to have it move left. So yeah, it's too quick to see. But the point is that every single time you call the step function, it runs the simulation 1 step with you putting this item in. So what we want to do is create some sort of policy that takes in the information and outputs which direction you should go, because you have to go either left or right. Those are your only options. You either go left or you go right. You accelerate left and accelerate right, rather. So I'm going to go ahead and write just like a basic policy. I will put it, I guess, right here. So our basic policy, just as an example, to kind of see a baseline of, how our AI is going to do, as well as just understand for us how this environment works. And I'm just going to say, all right, if the pull is tilted to the right, I'm going to move right. And if it's tilted to the left, I'm going to move left. That seems like a pretty good basic policy to follow. So I'm going to get that angle, and that's obs bracket 2. That's the third item in obs. And then I'm just going to return 0 if angle is less than 0, else 1. So yeah, if it's tilted to the left, go left. And if it's tilted to the right, go right. Any questions about that? All right. So now let's go ahead and run that whole simulation. So what I'm going to do is, I guess I'll just replace this for now. I'm just going to say for step in range 200, because 200 is the max you can go. If you get it this far, you've won anyways. But I'm going to figure out what action I want to take. And I'm just going to say that's the basic policy based on the observation, which is, again, just looks at the angle, it ignores everything else. If it's tilted to the left, it goes left. And if it's tilted to the right, it goes right. And then I need to actually perform a step with that. So that's the obs reward done info equals m.step. And then I'm going to input that action, whatever our policy decides. And then I'm going to go ahead and say that the rewards, I'm going to add the reward amount to that, which in our case, it's always going to be 1. Oh, whoops, I need to define rewards up here. You know what? Yeah. So it's always going to be 1 if we're continuing, but we don't necessarily know that about every environment. So we add our reward to the rewards. And then if we messed up, or if we've exceeded, if we've gotten to 200 steps, then it's going to say done inside. Yeah, it's going to give us done. So we basically just check if we're done, then we're going to break and end the loop. Okay, and then at the end of it, I'm just going to go ahead and print out the reward. And actually along the way, so I could run this and, see like, okay, good. Oops, not reward, it's rewards, plural. So we got, 42 there and 33 there. And I can go ahead and put m.render into here. It doesn't really matter where, but I guess I'll put it actually after all that logic to not break it up. So we can actually see it in action. So my cart, tries it for a little bit, but then it falls. This is the maximum threshold, so it only lasted for 52 steps. And then this one only lasted for 25. So it's not really a great policy, considering that the max is 100 or 200. We're not really getting anywhere close. And you can see why. It oscillates for a little bit, but it overcompensates for part of it. In fact, I'm going to go ahead and to make it a little more viewable, I'm going to import time, and then I'm going to say time.sleep 1/30th, so that it goes, 30 frames per second. Did I mess that up? No. So yeah, so this is a little clearer to see what's going on. I don't know how well y'all can see it over the Zoom lag, but you can do that on your own too if you'd like. We're going to take that out soon so that we can, run a whole bunch to train. But it moves left and right and goes a little too far. It goes a little farther each time until it just completely overdoes it and loses. And that happens really quickly. So now we'd want to train a neural network in order to figure this out. And our neural network is going to be very, very simple. Like I said, we're only going to use one TLU in it. And we're not even going to really have, we're going to kind of abstract away the TLU the way I like to do it. But we're going to go ahead and make a perceptron that's going to have some weights to output a result in the policy. So when I initialize the perceptron, it's going to be given some weights to start with because, again, we're using a genetic algorithm. So it's going to be given random weights initially, or if it is a child of a previously existing perceptron, then it's going to receive weights that are similar to its parent. So I'm going to first say self.weights equals weights, and then self dot, well, that'll come a little later. I guess I'll put it in self dot score so that later on it's just the easiest way to keep track of how each one has done. Whoops, so there we go. So yeah, so it's gonna take in some weights and then just save those, right? And then our policy is gonna be literally just to multiply each part of the observation by its corresponding weight, and then return 1 if that's greater than 0, and return 0 if it's less than 0. So I'm going to go ahead and define that policy here. So just the basic, simple Heaviside function. So based on the observation, which again is position, then velocity, then the pole angle, and then the pole's angular velocity. But that doesn't matter at all to the AI. These are just meaningless numbers. It will eventually figure out which ones are important and what values you want them to be at. But it doesn't really have any inherent value to the AI itself. So I'm going to go ahead and I'll expand this out. In my original, I have it very compact, but that's not really super readable. So I'll improve this a little bit. So I'm going to go ahead and say for I in range, I guess first I'll make a sum. So I'll say total equals 0. And then for I in range len obs. And our weights are going to be the same length. So every observation data point is going to have a corresponding weight. So we can just go through it one at a time. I'm just going to say total plus equals self.weights bracket I times obs bracket I. And then based on that weight, I'm going to return either 0 or 1. So I'll just return 0 if total is less than 0, else 1. Does that make sense? Okay. So now we have that. Let's go ahead and make a more complex function to actually evaluate how good a policy is. So I'm going to take this. So this goes through one episode. So I'm going to include that. Or maybe I'll take out this time.sleep and this render, and I'll put that inside a run episode function, and then I'll return the rewards instead of just printing it. So run episode based on some policy. And so instead of basic policy, I'm just going to change this to the general policy variable. And then at the end, I'm going to return the rewards. Got any questions about this? All right, cool. Oh, I forgot my colon. And so now, in order to evaluate a policy as a whole, so I'll say evaluate policy, I just got to run several episodes on it. So I'm going to say policy, and I should probably declare how many episodes I'm going to run. So I guess I'll define all my constants like right here. So yeah, num episodes, I guess. And I'm going to start with, I'll try like 10 episodes per policy to figure out its expected result. And I'm going to just run through every single policy. So I'm going to keep track of all of the totals. I guess, yeah, that's fine. So I'm going to keep track of all the totals inside a list, basically what each episode gave us. And then I'm going to go and actually run these episodes to make it happen. Oops, not 10. I want to use the constant. So for episode in range num episodes, we're just going to go ahead and run the episode. So I'm going to say totals.append run episode with that policy. And then at the end, all I have to do is just return the mean of those episodes. So mp.mean totals. So I'm going to go ahead and just create a bunch of random perceptrons and evaluate their policy. So first, I'm going to go ahead and I guess I'll also up here determine a generation size that we can change. And I'm going to start for now with like 10. So let's go ahead and create these perceptrons. So I'm going to say agents equals perceptron, and then parentheses. I'm just gonna gotta give it 4 random weights. So I'm gonna say random.uniform -1 to 1. The weights, like the numbers you put in here really don't matter as long as they're evenly distributed amongst positive and negative. Even that's not ultimately super critical. I guess in theory you can have any numbers, and eventually natural selection will get you in the right place. But the magnitudes of these numbers really don't matter at all, because all that matters is their ratios to each other. And either way, if you're doing it over a uniform distribution of the same one for each, then it doesn't actually matter. So I like to just start with -1 and 1. But keep in mind, these are like maximums for the starting value, but there is no maximum or minimum to what the weights could eventually become, depending on what equation you use to add that randomness between each generation. All right. So, yeah, we have this uniform random numbers. Oops, did I? Yeah, I did. This should go in here. So, and then we just want to make this happen for I in range 4. So this is, the perceptron. Oops. Oh yeah, for I in range 4. And then we want to just make, one generation of those. So I'm going to go ahead and say for j in range generation size. Any questions about that? Do you want me to, are you guys cool with those list comprehensions? Or do you want me to expand it out into a more readable for loop? All right, cool. Okay. So now we've got that. Let's go ahead and evaluate all of them. So let's just do that first step of figuring out which ones are the best. Oops. So I'm just going to say for agent in agents. And I'll just print out evaluate policy of its policy, agent.policy. All right, and now I'm going to go ahead and run this and see if I made any mistakes. Okay, cool. So yeah, it doesn't give the visuals of each one, but you can see that these random results, even with only 10, we have quite a range of results here. The best one actually got all the way up to 172, just with completely random numbers, and the worst one only got to 9. So you can see that the weights probably ended up in basically doing like pretty close to optimal, and then doing literally the worst thing it possibly can. I should actually print the weights for each one. That's probably a good idea. So agent.weights. And let's run it again. We may not get as interesting results. Okay, this one got 200 right off the bat. This is a simple enough problem that does happen. So this one got the max with these weights. And they also could have just gotten lucky in the 10 episodes. Like we made more episodes, their mean result might have been lower, but I imagine it wouldn't be that much lower. So you can kind of get a sense for this particular problem of which weights are important and how much they matter. So this one, very small. So the position of the cart doesn't really matter too much, at least with the approach that this is taking. And that's another thing, is that we could have two approaches that are optimal in these situations, in that they will reliably get 200 points. But that doesn't necessarily mean that that they aren't necessarily going to have the exact same approach. So we could end up with different sorts of weights, or it may not be scalable to a different sort of thing, where basically the small weights for the position are likely not to matter for our simulation, because it's hard to get all the way over in 200 steps. You basically got to kind of book it. And in that case, you probably drop the pole anyways. But it is conceivable that there would be a policy that might attempt to kind of shift the pole and then push it, like to keep it balanced, to keep that kind of, so it doesn't have to wiggle, it can just kind of go. And then that would have to care more about weight, or more about the position. Wait, yeah. So this one's position. This one didn't care much about position. It kind of thought equally about the angle and the velocity of the cart, of how much it matters. And it also thinks that the further right each one is, that makes you more likely to go right, which makes sense. If it was negative, it would be the opposite. But it really cared about the pole's angular velocity comparatively. It would, if the pole was going right, it would try to stop it from going right, without putting as much priority necessarily where the cart and the pole actually are. Though those are obviously very important. It's not like this, so about 0.8 isn't really that much bigger than 0.5 and 0.4, but you can kind of see the relative importance to these particular examples. Is that making sense? Any questions about that? All right, cool. So let's go ahead and take a break here, like a little 5-minute break, and then we will continue with this and actually start doing the genetic algorithm, the natural selection on these agents right afterwards. All right. All right. All right, so if you guys are still around, then please come on back. All right, welcome back. All right, so let me go ahead and share this again. Okay, so let's go ahead and actually start running the genetic algorithm on these agents. So basically each time it runs, after figuring out like what every agent's policy is or how well it scores, we want to record that and then choose the best ones and let those ones survive and kill all the other ones. So I'm going to go ahead and change this to, instead of just printing the policy or printing evaluate policy, I'm going to record it. I'm going to say agent, dot score equals evaluate policy, and then its policy. And then at the end of doing all of that, I'm going to go ahead and sort them all. I'm going to say agent dot sort. So I'm going to have to say, all right, we care about its policy, right? So key equals lambda agent and return its score. And I'm also going to want to do it in reverse order. So that the higher the score, the closer they are to the front of the list. Oops, this should be agents, not agent. So once we have that, well, I'm actually going to, oops. Yeah, no. Yeah, for now, we'll just keep on going. So what I want to do is put this inside a loop for one generation. So I'm going to add another constant for generations, num generations, I guess. And I'm going to also make this 10. We can play around with these numbers in a little bit. I'm going to say for I in range num generations. So evaluate every agent and then sort them. And then next up, I just need to remove all the ones that didn't make the cut. So I'm going to say agents equals agents bracket, and then just, cut out all but up to generation size divided by 5. So take 1/5 of them. And this number could change, but I think, like I said, that's a pretty good general guideline that I think it likes to be used, is keeping the top 20% does allow, like, it allows the best ones to survive while also keeping some diversity in the gene pool, so that you don't end up with just like, things that evolve purely from the first one that did the best at first, or the first few that did the best in the very beginning, although that's exactly what we're doing here, so we only have a generation size of 10. But yeah, it's a good rule of thumb. It is also sometimes a good idea to allow a small chance of a one that didn't perform well surviving, just again to keep that diversity, so that you don't necessarily get put into one specific type just because of how your random generations went in the beginning. We're not going to do that here, though. We're just going to take the top 20%. And now we just need to create all the new ones. So I'm going to say for agent in agents.copy. I got to make a copy of the list because I'm going to be modifying the list as I go. So I need to make a copy so I can iterate over it. I'm going to say for j, I got to use j because I use I up at the first loop in range. So just 4. So each agent is going to produce 4 descendants. And it's going to be asexual reproduction. That's just going to be the easiest here. So for now, I'm just going to put a pass because I want to put this function to create an offspring inside the agent itself. So I'm going to go ahead and go back up to the perceptron. And I'm going to define a spawn function. And inside the spawn function, I'm going to include a what's the word I'm looking for? Sorry, totally drawing a blank. A mutation rate. Basically, how quickly how quickly is it going to vary as we go from generation to generation? So now I want to go ahead and just create some sort of equation to figure out the new weights of the offspring. And this equation, I'm not really too sure what a standard one would be. Well, or like, I guess I am, but like a simple version. There, like, basically, there is no like standards. Really, what I'm trying to say. You could scale it based on the weight of, well, the weight itself. Basically, if it's already really prioritizing something, then the amount you change it by would be larger. And if something's small and is considered to be insignificant already, it's not going to change that. And that could be valuable, particularly later in the learning situation. So you don't randomly start doing new things that you shouldn't have been doing in the first place. But I think like we can play around with this equation, but I'm going to keep it simple. I'm just going to add a so take the existing. So I'm going to do a list cover edge of this. So w plus random dot uniform. Let me go ahead and move this over. So I'm going to make this larger. But ram dot uniform. Negative mutation rate, positive mutation rate for W in self dot weights. So basically, it's going to go through every weight in its own weights, and the offspring's weights are going to be its weights plus or minus the mutation rate. So the larger the mutation rate, the quicker, the more different that it's going to be from its parents. So I'm just going to then create a perceptron, a new perceptron, based on these weights. So we're going to put in the offspring weights in, and then we're good to go. All right. So now the perceptron is able to spawn newer versions of itself. And I'm going to go into here and just go ahead and agents.append, agent.spawn. And then the mutation rate I used when I was experimenting is 0.2. I mean, I experimented in a lot of, well, not very many, but I tried playing around with these numbers, and these are just what I found that gave good examples of growth that made it very clear what was happening. It wasn't necessarily the best growth, but it was very clear examples of growth. So with that, I'm going to go ahead and now at the end of doing all that, I guess technically we're doing one more step of this than we have to. Like we're regenerating the agents and calling them one more time than we have to. Well, yeah, because we don't actually do another test after this, but ease of coding. The expensive part, the hard part is actually testing. And so that part is fine. So I'm going to go ahead and print agents bracket 0.weights. So this is going to be the winner, right? This is the one that did the best in the last generation. Technically, there might be another one in this generation that's better than it, but we never ran the test for it, so that's fine. And then I'm going to go ahead and also run it one more time, but I want to actually see the results as we go. So I'm going to add in a into our run episode. I'm going to have a visual variable and set that equal to false. And by default, it's false. But then I'm going to say, so that here, I guess, if it's visual, then I'm going to say env.render. So this way, I can put out the weights, and then I will also let it go through it in action. So I'll print evaluate policy agents bracket 0 dot policy, and then true for saying we want the visual representation. I guess I'll also make it a little slower to yeah. So I'll put this time.sleep inside here. So I know I'm bouncing around a lot. I should probably be in a more consistent spot. So were you guys able to get all that? Is there a part of the code I should go to? All right. So we'll go ahead and run this now. I'm gonna run my generations, and we should have a print as it goes through them. That'll demonstrate the growth a lot better, because right now it just takes a while and then it crashes because is it evaluate policy, and then I put in yeah, this true should be right. It's not evaluate policy, it's well, I guess I see. Yeah, I did it a little differently. So we should put visual in here so we can pass it down. Visual equals true, and then pass visual into run episode. Oops, visual equals false is the default value. Is that what I set up there? Yeah. So there we go. That way I can put true into here. But also, let's make sure we print it as it goes, because it's like, okay, great. So what does this print here? I need to be more careful with these things. Is this the only print we do? See, are these the weights? Or did it do it multiple times? Oh. Okay, whatever. That's fine for now. Does evaluate policy return a whole? Okay, no, it just returns a mean. I'm not sure where all these statements are coming from. But the important thing is that we see the end result. So, I guess it just didn't clear from last time. That's all. That makes sense. So yeah, so now we see our perceptron in action, although it doesn't seem to be doing much because there's an error. Sleep takes, oh, whoops, I forgot to say how long to sleep for. This isn't Lua where you can it'll just give a default value. All right, so we run it, and then after several generations, see our cart is doing a lot better this time than the previous one. It's able to keep it going until, oh yeah. So we're actually doing, right, we're evaluating the policy with a whole bunch of them. So maybe better, rather than running the visual version of the whole evaluate policy where it's going to do 10 episodes, we can just print its score because it's already been evaluated in the last generation, and then just run one episode. So I'm going to go ahead and print. I'll print its weights and its score in together. So score weights, or agent.score rather. And then I'm going to not have this part be visual. I will just have it run run episode agent.policy and true for being visual. Yeah, although it is kind of good actually to see, 10 of them, and see that it was consistently able to do it, right? Its mean result was 200, and it pretty much never had any problems. So along the way, let's actually also, when we evaluate a generation, figure out what the best score of that generation was. So after each generation, we sort them and we rerun them, and it doesn't really matter. I guess I'll do this right after I sort. I'll print agents bracket 0 dot score. So this will make it a little more clear how it's progressing as we go. Okay, so see, this time I got really lucky or unlucky as far as the growth goes, and it just randomly created one that was perfect right at the beginning. In fact, I'll print the weights as well when we put this in. Score in agents bracket 0 dot weights. And let's hope that this one, okay. So you can see this is a relatively simple simulation. This is, I guess, a problem with that is that you can end up with basically if it really prioritizes the pole's position, that's what's happening here, right? And this was the big winner every time too. None of its offspring were able to beat it, as you can see that the weights haven't changed. And that's because, yeah, this just really, really cares about the pole's position and doesn't really care as much about everything else. It cares about its velocity. So yeah, if you end up with one like that, then it can end up being correct right at the beginning. So this one is a little more wobbly, but still does a good job. I'm going to go ahead and lower the generation size to, I don't know. Oh, yeah, this is ridiculous. I swear this was not how it was working. Okay, there we go. So we start out with one. Our best one was 88 at first in this example. Yeah, so our best one was 88. Maybe I'll add an extra print at the end of each run just so that we can distinguish between them. But our best run was 88 at first. Then it became 129. Then it upped itself. Basically each new generation got better and better quite quickly. For a simple problem like this, that worked out pretty well. Jeez. But yeah, do you have any questions about this? Were you guys able to get your genetic algorithm online and you're able to get these cute little AIs controlling the cart? All right, awesome. Yeah, so in that case, that's actually all I had. I expected it to take significantly longer. So Jenna, you can go ahead and get going here. You don't have to fill the rest of the time. That's okay. I do have other stuff, but I'm going to be kind of preparing in the background while you're doing your bit, Jenna.
Okay, well, Grant, do you know what the Turing test is?
Vaguely, yes.
Okay, so we'll just quickly talk about that. That's kind of what we're doing.
And the thing is, Jenna, there are a fair amount of people who watch these recordings, so you can still cater to them as well. It doesn't have to be just Grant, though. I would say he's the priority because he's here, but yeah,
it's for you. Okay, yeah, I forgot people do that. Okay, so we'll just quickly talk about the Turing test a little bit. So the overarching idea is, can machines actually think? As I said before, there's this kind of fear, and media has really pushed this idea that AI is going to take over the world, and all of a sudden it's going to take over humanity, kind of Westworld season 3 vibes, there's a fear that robots are going to get out of our control, but there's this big question of, can machines really think? We're coding them to do this algorithm and we're saying they're learning, but are they really learning and thinking on their own, or are they just following the algorithm? So that is what the Turing test is trying to solve. So it's the best known behavioral test for consciousness, which was put forward by Alan Turing in 1950 as an answer to this question. So who is Alan Turing? It's this guy right here. He was born in 1912 and he died in 54, pretty young, and that was due to like social issues mostly. But he was an English mathematician, computer scientist, logician, cryptanalyst, can't even say the words anymore, philosopher, and theoretical biologist. He laid numerous foundational stones of modern computing, ranging from the deepest mathematical nature of computing using what are now called Turing machines. He provided the modern approach to incompleteness and undecidability. To specific issues of practical design, he also contributed to mathematical biology, morphology, and much else. But what most people know him by is his key role in the British government's breaking of the German Enigma code, and the what's it called? Oh my god, I just blanked. The Impossible Game. What's it? The movie with Benedict Cumberbatch.
The Imitation Game.
Imitation Game. Thank you. But the Turing test is still a thing today. Like, for instance, I believe the CAPTCHA that everyone has to do, where it's like the robot test, where you have to click all the cars and stuff. The T actually stands for Turing, which I believe that's true, but to my knowledge, it is. So what is the test? So the Turing test is deceptively simple method of determining whether a machine can demonstrate human intelligence. So the rough idea is you place a computer and a human on one side and a human evaluator on the other side. If the evaluator can't recognize which one is human and which one is computer after a series of questions, then the computer successfully passed the test. And the rough idea is just, can a machine engage in a conversation with a human without being demonstrated as, without being detected as a machine? If so, then it has demonstrated human intelligence. So to illustrate this a little more, this is kind of what it would look like. So during the test, we have our evaluator right here, and we have our human respondent and our computer respondent. And do they not? Okay, there we go. And we're just kind of comparing the differences between machines of like computational ability. Humans are slow and likely to make mistakes, where machines are fast and nearly flawless. Random number generators, we trend to spread out, while they are less likely to spread out. All of these things are different things that you would take into consideration in trying to determine if this was a computer or human, because AI is supposed to be like kind of based on humans, but we're very different in all these ways. Yeah, so here's like some examples of like some tasks they would do. So for instance, we'll just look at like this one. It's Mary went to the bathroom, John moved to the hallway, Mary traveled to the office, where's Mary? So it's like basic comprehension and following the story. And yeah. So has any machine passed? At the moment, no machine has successfully passed, but we have come really, really close. So I'm going to go through 4 examples of machines that have gotten close and what they did. So first we have ELIZA. ELIZA was made in 1966 by Joseph, I'm not going to pronounce his last name. And then this program looked for specific keywords and typed comments to transform them into sentences. Its script pretended to be a psychotherapist that gave non-directional responses. If ELIZA couldn't find a keyword in the user's text, it would provide a non-directional response containing a keyword from earlier. So it would kind of like act as if it was really listening, but it was just finding these trigger words. And that's why it could fool some humans. And they claim to be one of the programs to pass the Turing test, but I think that's kind of up for debate. I mean, I personally would say it didn't, but different theorists have different ideas. And ELIZA was an easy target if trying to intentionally ask questions that are likely to make a computer slip. So this is one of the things that I like to do with students is like go to chatbots and see what we can come up with to make them like show themselves as a computer, and the idea of like, what is a question that can prove you're human? Like where is that lie? So that's a really fun thing to explore. And ELIZA is a very clear target of, you could ask them something that doesn't completely make sense, but a human would be able to get it and they would probably slip up. So here's just a video to explain it. I don't know if I'm sharing sound, so we'll see in a second.
Does it understand what it's doing in the sense that we do? It's easy to leap to false conclusions, as Professor Weizenbaum discovered when he created ELIZA. ELIZA is a computer program that anyone can converse with via the keyboard, and it'll reply on the screen. We've added human speech to make the conversation more clear.
Men are all alike.
In what way?
They're always bugging us about something or other.
Can you think of a specific example?
Well, my boyfriend made me come here.
Your boyfriend made you come here.
He says I'm depressed much of the time.
I'm sorry to hear that you're depressed.
It's true. I am unhappy.
Do you think coming here will help you not to be unhappy?
The computer's replies seem very understanding, but this program is merely triggered by certain phrases to come out with stock responses. Nevertheless, Weizenbaum's secretary fell under the spell of the machine.
I asked her to my office and sat her down at the keyboard, and then she began to type. And of course, I looked over her shoulder to make sure that everything was operating properly. After 2 or 3 interchanges with the machine, she turned to me and she said, "Would you mind leaving the room, please?"
And yet she knew, as Weizenbaum did, that ELIZA didn't understand a single word that was being typed into it.
You're like my father in some ways. You don't argue with me.
Why do you think I don't argue with you?
You're afraid of me.
Does it please you to think I'm afraid of you?
My father's afraid of everybody. My father's afraid of everybody.
Okay, so that's ELIZA. I don't know how to get out of this. Where's the next button? No. I feel like Nick right now.
What the heck?
Feel like you. Okay.
Oh, I feel so attacked for no reason.
It's out of love. It's out of love. So another, sorry, Nick. Another AI that has been almost past it is Perry, which was in 1972. And Perry was a chat box modeling the behavior of a paranoid schizophrenic, and used a very similar approach to that of ELIZA. And during the Turing test, 2 groups of psychiatrists analyzed the conversation transcripts of both actual patients and computers running Perry, and 48% of the psychiatrists were fooled 48% of the time, which is pretty impressive considering like that's their whole job. Oh, I accidentally left that in. Ignore that. Don't worry about that last one. The next one was Eugene Goostman, which I think is just a really funny name. And this was in 2014, and it's a computer program that simulated a 13-year-old boy from Ukraine. And a lot of headlines stated that it did pass the Turing test because the bot convinced 33% of the human judges that it was human. However, there were only 3 judges, meaning that only 1 was fooled. So that's not like super statistically significant. Another problem was that by portraying that chat box as a 13-year-old child, judges would let nonsense sentences and obvious mistakes slip because they thought it was just English skills and young age. So who's to say? But here is one of the most recent AI assistants that people think will pass the Turing test. So let me...
When we started, we made this for everyone, so that everyone could find anything they need among the millions of bazillions of things in the world. Today, it seems like sometimes it's easy to feel like you need a little help with the stuff just in your own world. Your photos, phone, videos, calendars, messages, friends, trips, reservations, and so on and so on. Wouldn't it be nice if you had some help with all that? Wouldn't it be nice if you had a Google for your world? That's why we're building the Google Assistant. Hi, Amy. How can I help? You just ask it what you need. Okay, Google, what do I have to do today? And your assistant understands and helps you out. You can even carry on a conversation with it. How long will it take to get to downtown Chicago from home? Here you go. What restaurants are there? Book a table at Cortino Restaurant. Sure. And the assistant is always there for you. So if you're on the road, you can ask it where to fill up. And if you're at home, you can ask it to play some music. Or if you're in a chat with a friend, it can show you what's playing tonight. It's like your own personal Google. Naturally, anything you share with it is safe and secure. And the more you use your Google Assistant, the more useful it becomes. Remember, my byte combo is 326. Got it. And soon, you'll be able to access it from all sorts of places, so it will be everywhere you are. We made this for everyone. And today, we're making this just for you. Hi, how can I help? Meet your Google Assistant.
Awesome. So yeah, so I suggest looking at videos of the Google Duplex calling different places to make reservations. It's pretty ridiculous how many like how I keep saying that's a very human thing, and the Google Duplex will actually do that and has a lot of good pauses. And I think if they called me, I'd be pretty well convinced. So the Google Duplex is from 2018, and it called a hairdresser and successfully made an appointment in front of the audience. And the hairdresser did not recognize that she was speaking to an AI, which is pretty groundbreaking considering like AI voices kind of have sounded very robot-y for a while. So people are like, they're pretty far from still passing the test, but I would say out of all of them, they're the most likely to and will. So when should we expect machines to actually be able to pass this test? And some suggest that it might not happen. It might happen around 2030, but some say not earlier than 2040. But the overall consensus is that we need to know more about the human brain before replicating something we still don't fully understand. So like I said on the first day of class, it's like, and as we saw today, like the neural networks are based on real neurons, but it's actually ridiculous how much of our brains we don't know. I had a professor say we know more about the oceans than our own brain, which like everyone always knows that the oceans is like so unknown considering we've lived here for all this time and it's so close. But we still don't know a lot about our brains. There's so many functions we don't understand, and we're just making hypotheses still. So we need to first learn more about ourselves before we can implement this and get machines that can truly think. So in summary, Alan Turing used natural human brain intelligence as the prototype for artificial intelligence. Previously, AI researchers have largely ignored the brain as a source of algorithm ideas, lacking the means to analyze the brain properly. Today, we can look inside our biological black box to find the answers and build intelligence and fair artificial systems. So how can you prove you're a human? This is one of my favorite questions, just something to think about. And here are some different chat box. So you can directly talk to Eliza or Alice, Elbot, or Cleverbot. I think Cleverbot's my favorite, but he's sometimes a little moody or sassy. So be a little aware of that if you're showing it to an audience. Or if you want to take your own Turing test, I saw this was really cool, of a visual Turing test, just so you could get a good sense of it. So if you're ever bored, talking to chatbots are kind of fun, and kind of fun to do your own little Turing test. Do you have any questions, comments, or anything like that? Awesome. So I will be sharing this. I put this in the 2 videos in a drive. I'll be sharing it with everyone, just so if anyone wants to do a little Turing test talk, I got you. So yeah.
Thank you, Jenna. This workshop as a whole has pretty much entirely been about machine learning in some capacity, but that's not the entire field of AI. There are, AI as a whole is really just, what Jenna just talked about, right? Like trying to make computers act intelligent, and that doesn't necessarily only entail machine learning. So I wanted to take some time to make a tic-tac-toe AI that uses a Minimax search algorithm to determine every possible outcome and to pick the best one. Is this something you've done before, Grant?
Oh, I haven't done this. before.
Okay, that's good. That's good. So yeah, hopefully we'll be able to do it in 20 minutes, but at least we can start on it. So I just coded up this REPL, so you can go ahead and fork it. So it's not the most elegant because I just made it right now, so I apologize for that. But I think it works. I'm pretty sure it works from testing it real quick. But basically, I guess I'll go ahead and share this as well. So let me go ahead and share my screen. All right. So what we want to do is right now the computer player just picks randomly. It double checks that it's a valid move because that's another problem with that I need to add into the game, but it doesn't. Our game itself doesn't check if the move is valid. Also, why is this a exclamation mark? That should be that thing. But it just picks a random move, right? So let's make it smart. Let's make it so that it can figure out the best possible move. And the way it'll do that is to just kind of go through and evaluate the board state and return the best move based on that. So I'm going to go ahead and first make a dummy function, evaluate board, and then it's also going to take in the player so it can figure out which player is evaluating, right? So it can say whether you're whether it's a good board for them or a bad board. And for now, I'm just going to say pass. But the basic idea of the computer move that we want to do, or I'll just, I guess I'll return one. So that'll say every board is a good board for now, and this dummy function. So we can write our computer move function, and then we'll improve the evaluate function a little later on. So the idea, if you want to figure out the best move, is to just go through every possible move and evaluate the board. So the computer move doesn't take in a board, so I'm going to go ahead and make a copy of the board so I can change it without actually affecting the real board state. So I'm going to say in here, copy equals board.copy. And then I'm going to go ahead and make a bunch of moves on this copy. So I'm going to say for move in range len copy, I guess. So the idea here is we're going to go through every move. And by the way the moves work, there's just 0 through 8, where 0 is the top left corner, 8 is the bottom right, and it goes left to right and then down. So I'm going to go ahead and make that move. So I should have a variable for who the computer player actually is. Do I have that? No, it's just the computer is always player 1. Okay, that's fine. For now, I'll leave that in there. So for every move, we're going to go ahead and evaluate the board for the computer player. So I'm going to say, I'm going to be keeping track of the best state so far, and I'm going to start with a number that is impossible. So basically what I'm going to, the system I'm going to use is that if it's a winning board, like a guaranteed win for the player, it's a 1. And if it's a guaranteed tie, it's a 0. And if it's a guaranteed loss, it's a -1. So you may be asking, I just gave 3 guaranteed options. Well, there's obviously, no guarantees in the entire game. But in order to run this algorithm, we assume that the player is going to take their best possible move. So with that assumption, some outcome is guaranteed on every single board. If you assume that both you and the opponent player are going to take the best possible move, then there is going to be an end result. There is one specific path, or at least there could be, equal paths, but the point is there is one specific outcome. It's going to be a win, loss, or tie with that assumption. And if your opponent happens to mess up and make a worse move, then great. That's, if it's a worse move, that means it's better for you. And then you can reevaluate and based on that. But if we assume that the opponent is going to make the best possible move, it's going to return a -1, 0, or 1 based on whether that board state will result in a tie. So I'm going to go ahead and say current equals evaluate, on the copy, but I guess actually first I'm going to have to make the move. I'm going to have to check to see if the move is valid. I'm going to say if copy bracket move does not equal a blank square. So if it's not blank, then I'm going to make the move. So I'm going to say copy bracket move equals player 1 because that's the computer player. And then after I evaluate it, I'm going to check to see if it's the best one so far. I'm going to say best equals max of best so far and current. And since I initially set the best to an impossibly low value, that means it's guaranteed that if there's a valid move and we see it, it's going to choose one of them as the best move. So I'm going to need to record that as well. I guess I should call these best value and best move, so that you not only keep track of the best value, but which move actually gives you that value. And I'm gonna again have this be an impossible move. This doesn't matter as much because it should get replaced by whatever the actual best move is, but I'm just gonna make it impossible so that if we get that, we know there's something wrong. So the best value and versus the current value, and then I guess I would need to, rather than forming the max initially, I'll need to check to see if it is the better value. So I gotta say if current is greater than the best value, then we'll just go ahead and save the best value as the current. And the best move as the move that we're looking at. Does that make sense?
Nick, on line 28, should that be 1 equal sign?
Yes, thank you.
Awesome.
Yep. Cool. So yeah, so we figure out the best move by going through all these moves, evaluating the board state, and then saving that move. And then at the end, we'll have the best move stored, right? So I can just return move at the end. And if we have an best move rather, if we have an evaluate function that works, then this is going to find the best move. Does that make sense? Basically, go through every move and evaluate it. And if it's the best move, return it once you've checked all of them. So the crazy part happens inside the evaluate function, where basically in order to evaluate a board, you act like you are the other player. You consider, what is this situation? What does this look like if the other player makes their move? And I'm realizing I actually did make one mistake here. I'm going to need to undo the move inside the copy after making the move. So I'm going to say, after evaluating, I'm going to say copy bracket move equals blank to undo that so it doesn't overwrite. So in order to evaluate it, it's going to start out the exact same way. It's going to be very, very similar, actually. I'm going to make a copy of the board that I was given. It's almost exactly the same, actually, but there is a key difference, which is why it has to be a separate function. I'm going to figure out what the best value is. And I actually don't care about what the best move is. I'm just looking at the board, right? I don't need to return the best move later, so I don't need to keep track of this down here, but I do still need to keep track of the best value. And I'm going to go ahead and go through every single move. So I'm going to say for move in range len copy, and I'm going to figure out, I'm going to go ahead and make the move. If copy bracket move does not equal blank. I'm gonna make the move. So these are all the same as lower down. So I'm gonna say just player, right? Because this is now general. This isn't just the computer. This is gonna be for either player. And here's where things get different. To evaluate the board state, I'm going to take the negative of the player. So, or I'm going to take the negative of what the other player wants to do. So I'm going to evaluate it for as if I was the other player and then reverse that. So current equals negative evaluate copy, and I need to pass in the other player, which I realize I left out of there. So copy, and then I have a function for the other player. And then here I'm going to evaluate copy, and then I'm just going to put in player 1. No, actually, because that'll make 2 moves rule. So I guess I got to do the same thing here. I got to do negative evaluate, and then I'll put in player 0. So I'm making like the opposite move here. And so that's basically how the evaluate moves through. Is I take the current player, and then I evaluate the other player's board and take the opposite of that. And then I have to undo. And then at the end, well, I'll do the same thing. Although I don't actually need to save the best move. I just need to remember what it is. So here I actually can say best value equals current or max current and best value. And then at the end, I just return that. So now this recursion here, obviously it doesn't have a base case, so we're going to need to add that in. So this figures out the best value for that player. So the base case is pretty straightforward. First, we need to see if there's a tie. Well, the tie actually comes last because the tie just checks to see that there's no state, no spaces. And so we should check winners first in case someone won the last one. So I'll say if winner, so if there's a winner for the board that I was just given, for the player who's evaluating their own board, it's going to go ahead and return 1. And then if the other player won, I'm going to return -1. And then if it's a tie, then I'm going to return 0. Is all making sense so far?
So for line 22, you said it's for the other player, but we just
Oh,
get
yeah.
okay.
Yeah, good catch. Yep.
Okay, cool.
This one actually technically doesn't matter. It's more there for the concept because the other player didn't just make their move. If you're checking this, you're checking for the one who just made their move. But that is not making excuses there. Yeah, you're absolutely right. So it's glad. I'm glad that you caught that because we probably wouldn't have seen it. So yeah, let's go ahead and run this and see what happens. Let's see if I made any mistakes here. So yeah, the computer move is just taken into here. So now if I run it, I'm going to go ahead and move to the 4. Yep. Okay. There was a problem. Maximum recursion depth exceeded. So something went wrong with checking here. It should have eventually gotten to a tie, but player. Okay, let's have it print out the boards as it goes. Sorry about this. If we don't get it done in the next 5 minutes, because I was kind of trying to go real quickly to fill the time, it's not a huge surprise here. I'll go ahead and post corrected code later on. Oops, why did I do player? All right. So let's see what it checks. So it Okay, it's just checking back and forth between the different boards. It doesn't seem to be actually making the move. Did I pass in the board instead of the copy? No. So for each move, I check to see if it's valid. Oh wait, whoops. I should only do it if it is blank. Yeah, okay, that looks better. I'm not gonna wait for all those prints to happen. Let's just see what happens here and see the results. All right, 4. All right, so yeah, it takes a little while, but it eventually figures out it's going to go to this corner here. And now I'm gonna go ahead and go to 0. And it blocked me. So now I'm gonna test this out to see if this is actually going to work. I'm gonna make a mistake here. I'm gonna go to move 6, and yeah, it blocked me instead of winning the game. So I think there is something up with it. But yeah, I'm gonna go ahead and not just have us sit here while I try to debug it. I think we're close enough to the end that I think we can end it here. But yeah, Grant, do you have any last minute questions, or do you understand like the concept of this? Obviously, the fact that the code isn't quite there is a bummer, and kind of breeze through a pretty difficult concept. But
Yeah, that was a little bit fast. I'll have to look
Yeah.
over the code when you get
yeah,
the
no worries. You can always talk with me about it later. I can give a more detailed description. It's just since we ended up at kind of this awkward point of like, oh, I don't want to not fill this time, but I also it's a little fast for this. That's how we ended up with this. But yeah, maybe I'll have a separate workshop on it, or you can come to my office hours and we can talk about it. And I will regardless post completed code in the Discord for both you and anyone else who watches this later, so that they don't have to deal with it, along with an explanation of what went wrong.
All right.
Yeah, cool.
Thank
So
you.
thank you.
Yeah, thanks a ton.
Yeah.
Bye now. Bye,
Yeah,
Grant.
and thank you, Jenna. Thank you, Grant, for being here. See ya.
Bye.